So, good evening, everyone. Welcome to the 12th and the final live session for the course Concrete Technology offered by NPTEL. I am Harshit Agrawal, a PMRF PhD scholar from the Department of Civil Engineering, IIT Bombay. So, in today's session, we'll first revisit the last live session that was for week 11 content in a quick recap manner, and then we'll look into the things that was covered in week 12 content. So, the week 12 content that we'll discuss today, we'll discuss about special purpose concrete, covering the leftover part from week 11 content, and then going through the week 12 content. So, for this, the session is divided into following sections. First, we'll talk about an overview of special purpose concrete, then high strength concrete, ultra high performance concrete, self compacting concrete, fiber reinforced concrete, roller compacted concrete, heavy concrete, lightweight concrete, and recycled aggregate concrete. So, these are like different types of special purpose concrete that we'll discuss today. In between, we will have some objective questions, like around 20 to 25 questions in total, that will challenge your understanding related to each of the concrete type. And finally, we'll conclude the discussion and the course, and I will try to address any other queries post discussion. So last week we continued to discuss about corrosion in reinforced concrete structure. We discussed about chloride induced corrosion, what are the sources of chloride ions for ingress through concrete cover. We discussed how chloride ion moves through concrete cover, the initiation phase, how it is detected by different parameters like surface chloride concentration, cover depth, critical chloride concentration, and diffusion coefficient, and what happens once the corrosion has initiated. So, for predicting chloride diffusion coefficient, we saw how fix second law which is used to model the non-steady state diffusion process, and how using certain boundary condition and assumption we can, using fixed second law, we can model chloride diffusion through concrete. We talked about bulk diffusion testing as per ASTM C1556, which is used to predict chloride ion diffusion coefficient. And then we saw research data showing the effect of SCM and concrete age, both on the diffusion coefficient value and the probabilistic service life of concrete. Then we moved into understanding the science behind corrosion, which is the electrochemistry of corrosion reaction. In this, we first understood what electrode potential is by understanding the activity that is happening at the steel electrolyte interface. We talked about standard electrode potential and saw how Nernst equation can be derived from Gibbs free energy to calculate the electrode potential of a electrochemical system in a given condition. And for that, we saw one example how that equation is executed for calculating a electrode potential value. We talked about application of electrode potential by developing pore-based diagram for a metal, which helps us to predict the stability of a metal in terms of potential and pH condition. And for pore-based diagram, we saw two examples, nickel and iron. And then for iron, we understood how pore-based diagram helps in determining the different stability zone. So like here you can see green is the passivation area, red is the corroded area, and blue is the stable metal area. So this we derived from pore-based diagram. Then we came into kinetics of corrosion, where we first derived the Butler-Volmer equation and then saw two special cases of this equation depending upon the amount of polarization we are providing. So first, when we provide a very high polarization, then we get slope constant and Taffel's extrapolation curve. And when we provide very small polarization, then we get Stern-Gary relationship, which can be used to calculate the polarization resistance if I-core value, that is corrosion current, and Tafel slope parameter is known. We understood how what is the application of this Taffel's extrapolation in Evans diagram, which is used to study a mixed electrode system. One example that we saw for this was how why zinc is nobler compared to iron using Evans diagram. So you can see here we saw that the corrosion current density of zinc is much lower than that of iron, and that's why it is nobler compared to iron. We understood the final application of corrosion kinetics for calculating corrosion rate, which is based on Faraday's law. And we saw 3 to 4 numericals to understand the entire kinetics concept post the discussion of Faraday's law. Now, with the understanding of corrosion chemistry, we talked about different ways in which corrosion can be controlled, which is divided into 3 categories: the cathodic process control, the anodic process control, and the metallurgical method. So, we saw what are different ways in each of these category. And finally, to end the discussion on corrosion, we talked about the role of concrete in controlling corrosion. So, we discussed how porosity, permeability, concrete cover quality in depth, and the near surface properties at the concrete cover can affect the initiation as well as the propagation period of corrosion in reinforced concrete. Okay, so this was all that we discussed in the last live session, mainly related to corrosion. Now, the final part of this course is about special purpose concrete. So, till date, we have always talked about conventional concrete, its mechanical properties and its durability properties. However, often based on the application demand, we may need to prepare a specific composition of concrete which is not prepared for common practice. And all these types of concrete which has some specific purpose comes under the category of special purpose concrete. Okay, so special purpose concrete, the special concrete, just a minute, my mouse pointer is not showing. Okay, yeah. So, special concrete refers to the concrete that is engineered for specific application and properties beyond what's provided by conventional concrete. Okay, and it is not just about the strength. So, when we talk about special concrete, it is not just about the strength, but it's about meeting the required unique project demand. Whether it's the lightweight construction or extreme durability or thermal insulation or even aesthetic requirement. So, we should not get this myth in our mind that it is just about the strength. When we talk about some special concrete, there can be n number of different objectives also which may be unique based on project demand, and all these things comes under special purpose concrete. Okay, now how this special purpose concrete is achieved. So using certain chemical admixtures like superplasticizer or retarders, or supplementary cementitious material like silica, fume fly ash, GGBFS, some custom aggregates like lightweight, heavyweight, or reactive type, some modification in the mix design to control W by C ratio setting time, or some specific curing technique to tailor a special purpose. So this special purpose concrete is like a unique blend of different components that we add in concrete, which is not generally or very conventionally used in normal concrete. Okay, so this table just gives an overview of some of the common categories of special purpose concrete, how they are described and what are their key features. So you can see high strength concrete. It is refers to a concrete with compression more than M55 grade as per IS 456, and its key feature is the load bearing capacity, the enhanced load bearing capacity. Then we have high performance concrete, which has enhanced performance in several areas like durability or workability. And what is its key feature? It is the overall quality with respect to demand or condition. So suppose I am present in a very severe exposure condition, then durability will be my demand. Or if I want a concrete which should be highly workable, then workability will be my demand, and that will relate to its high performance in that condition. Okay, then there's lightweight concrete, which is made of lightweight aggregates like clay and pumice, and which reduces the dead load of the structure. Mainly, these such concrete comes into application in high-rise buildings at higher floors. Okay, then there is self-compacting concrete, which flows under its own weight without vibration, so it has high workability, a kind of high-performance concrete only. Then there is air entrained concrete, which contain tiny air bubbles for freeze-thaw resistance, and which has a feature of durability, enhanced durability in cold climatic conditions. So we have talked about air entrained admixture. Okay, and that is what is used in making an air entrained concrete. Then there is fiber reinforced concrete, which uses fibers as a mixture design component, and that fibers help to resist crack and provides a enhanced post peak behavior to concrete. There's roller compacted concrete, which is a very dry mix concrete compacted with rollers, and it is used specifically in dams and pavement. Then there's pre-stressed concrete, where internal stress is introduced in the reinforcement before loading, which helps to improve the structural efficiency. There's reactive powder concrete, which has a ultra high strength and durability, and it is used for some special advanced structural application. Okay, so you can see there can be n number of special purpose concrete based on their quality that they possess and the area of their application. So now, just to have a quick overview on some of the special purpose concrete, we'll have just a quick overview on some of these special purpose concrete, and we'll first start with the high strength concrete. Okay, so high strength concrete is defined as a concrete having compressive strength more than M55 grade. If you can see this table, which is present in IS 456. Okay, so table to IS 456, it describes high strength concrete as a concrete which is having which is graded as more than M55 grade. So from M60 grade, high strength concrete starts. Okay, and such concretes are commonly used in advanced structural application where highest strength demand of 60 to 100 MPa is common. Some examples can be like high-rise buildings or bridges under extreme exposure condition, where use of high strength concrete has become very normal now. Now, when we use high strength concrete, it is used when normal concrete can't handle the structural load or the environmental demand. Okay, and there are four key features that may that defines that is key for high strength concreting. What are these key features? First is the pore refinement. So lower is the porosity, we know higher will be the strength. Then lower water to cement ratio. Again, will be the water to cement ratio, higher will be the strength, that we have now understood very well. Then use of high range water reducing admixtures. So use of high range water reducers helps us to decrease the water demand, and if we will decrease the water demand, it will help us to increase the strength. Okay, and since we are using admixture, we will able to maintain a particular workability without using any additional water. And fourth key feature of achieving high strength concreting is optimized aggregate skeleton packing. Okay, this ensures that there are minimum voids inside the concrete, and thus there is less water demand to achieve a certain workability. Okay, so these four are the key features for making a concrete high strength. Now, compared to conventional concrete, which is typically a four component system, a high strength concrete is typically a five component system. Okay, and which are key in achieving high performance and high strength. So in lecture you saw this was written as 6 because this separated 10 coarse aggregate and 20 coarse aggregate separately. Sorry, fine aggregate and coarse aggregate they took separately, but I have clubbed both the things into a single heading, that is aggregates. That's why I'm saying 5 component system. Okay, so you can see very specific demands of 5 component system that is required for high strength concreting. Like for aggregates, we use generally smaller maximum aggregate size so that we can achieve better packing and lower porosity. Why? Because larger aggregate can weaken the transition zone, the ITZ. Okay, and that's why we prefer to have lower aggregate size with high quality well graded aggregate and having improved packing density. Okay, so this is the demand of aggregate that we need for high strength concrete. In terms of cement, we need cement which has a highest early strength, like type 3 ASTM cement or blended cement. They are preferred for such high strength concrete, and we use high cement content, and we use high cement content to boost the strength. But with high cement content, there can be risk of increased heat of hydration and shrinkage also, that we need to control. For water, we must keep it very low, typically 0.25 to 0.35. And what this does, lowered water to cement ratio results in denser microstructure, which helps in higher strength and durability. Mineral admixture, these are generally used when we talk about high strength concrete. So use of silica fume is a must for achieving high strength. Why? Because it is extremely fine pozzolon, which improves the microstructure, reduces the porosity, and increases the strength and the durability. And typically 5 to 10% of silica fume is added by weight of cement for achieving high strength concrete. Okay, chemical admixture, again it is essential to maintain the workability with low water to cement ratio. Its dosage can range from 1% to 2% by weight of cementitious material. And what is the use of chemical admixture? It helps us to provide the flowable, cohesive, and dense mix without adding water. Okay, so these are like five key components of a high strength concrete mix. Now, often high strength concrete is seen with the myth that strength is all about the cement paste composition. Okay, here also mostly we have talked about, like in this entire section, we were talking about the cement paste composition only. Okay, but in reality, it is not just about the paste composition, but it is also about the aggregate quality. So, if you see a normal concrete like here, the stress versus strain behavior of concrete lies between cement paste and aggregate. Okay, so if we try to understand this, aggregate is what is making concrete superior in terms of stress versus strain distribution, while cement paste is the weak part. But now in high strength concrete, what is happening? What happens that the cement paste quality is improved. So you can see from here to here, my cement paste quality has improved. So the stress strain behavior of aggregate, concrete, and cement paste, they now lie in a very close proximity. But here also, if we improve the strength quality of aggregate further, we can improve the quality or the performance of concrete also further. Okay, so it is not just about the cement paste, but it is also about the aggregate quality that we are using, which makes a high strength concrete. Okay, so if we compare the stress strain behavior between a conventional concrete and a high strength concrete shows higher capability of withstanding stress. Okay, so you can see here it has a high ultimate strength stress value compared to a normal concrete. However, the strain at failure is much lower. So you can see here only the failure is happening, while in normal concrete the failure is happening here. So the strain is much lower compared to normal concrete because of the brittleness that is imparted by the stiff aggregate and dense cement paste system. Okay, so though it has a higher strength, but it will now fail in a brittle manner. That is one of the key properties of a high strength concrete. Now, how high strength concrete performs for different properties apart from strength. So this table shows concrete with different W by C ratio from 0.26 to 0.75, and you can see different features of the concrete with varying W by C ratio. Okay, so as you can see RCPT value, okay, are much lower for a low W by C ratio. So okay, so this RCPT test is a test which is used to check the chloride penetration ability through concrete, and lower is the RCPT value, denser is the concrete. So you can see RCPT value for 0.26 to 0.28 W by C ratio, these are very low. Okay, and they will increase as the W by C ratio increases. So this shows that the density of my concrete is denser when the W by C ratio is low. Then after 90 days, chloride bonding percentage chloride concentration at a particular depth is much lower for low W by C ratio. So we saw in the last session ACE team C1556 testing. The same here is used to calculate the chloride concentration at a depth like maybe 15 mm or 20 mm. So high strength concrete being denser shows it slows down the ingress of chloride ions and thus result in lower chloride ions at a particular depth. Then water permeability and air permeability of high strength concrete are much lower. You can see here the air permeability value is much lower compared to the values which are there at higher W by C ratio. And the same is the case with water permeability. It was not detectable uh, initially for very low water to cement ratio, but as the water to cement ratio increases, the water permeability also increases. Porosity, again you can see it is much lower for a high strength concrete compared to conventional concrete, and the same is the case with the permeability. It is much lower in high strength concrete. So all in all, since high strength concrete has a denser microstructure, its pore refinement ability enhances the property of concrete compared to conventional concrete. Another properties, if we see the creep, so lower creep, the high strength concrete has lower creep compared to normal strength concrete due to denser microstructure and lower W by C ratio. In terms of shrinkage, there is a controversial comments. Okay, the comments are not the same. Okay, so if you see autogeneous shrinkage, it is significant in high strength concrete. Why? Because there is very low W by C ratio and very high binder content. So we have seen what is autogeneous shrinkage. It is due to the chemical reaction that is happening between the cement and the water, which decreases the volume. So initially unhydrated cement paste has a higher volume compared to hydrated cement paste. So that's why, since there is more cement, then there will be more hydration that is happening, and that's why there is more autogeneous shrinkage in high strength concrete. While drying shrinkage reduces compared to normal strength concrete due to low permeability, but restrained cracking is still a concern in high strength concrete. In terms of fire resistance, high strength concrete performance is poorer compared to conventional concrete. Why? Because they're of the low permeability, the high density, and the low moisture escape path. So since my strength concrete is very dense, what happens when there's fire? So water is converting into steam, but the steam is not finding any path to move out. So they will generate internal stresses and they can damage the structure in case of high strength concrete. Whereas in conventional concrete, there are interconnected path through which the steams can escape, and thus it does not damage the concrete that much that can happen in a high strength concrete. Okay, now after high strength concrete, we will now look at some ultra high performance concrete. So in this first one is the micro defect free concrete, which is designated as MDF concrete. Okay, so first up, as a matter of fact, this MDF concrete was originally developed by these two scientists in 1982 to study the role of micro defect in strength reduction, which paved the way for ultra high performance concrete in today's world. Okay, so MDF concrete is is a ultra dense cementitious material which is engineered to eliminate microstructural flaws such as pores and cracks, which enhances the mechanical and the durability performance. Okay, now what are the key characteristics of such this MDF concrete? It has a ultra low porosity due to dense mix with minimal micro cracks or void. It has a very high binder content, typically uses silica fume, and a very low W by C ratio, even below 0.25. Okay, and it has a optimized particle packing which enhances the compaction and reduces the capillary pore. So all in all, what these steps are doing, it is decreasing the presence of void inside the system, which is making my concrete almost void free. Okay, and how this is achieved? By using binder system containing Portland cement and silica fume, by using super plasticizer to maintain the required amount of workability, by using very fine sand and no coarse aggregate at all, so that there is no weak ITZ uh, present in the system, and using sometimes using polymers like acrylics, epoxy resin, latex. They can also be used to enhance the workability, bond, and the chemical resistance property, but this is optional. The last point is optional. The other 3 points are key for making a micro defect free concrete. Next one in the ultra high performance concrete is the densified with small particle concrete, which is designated as DSP concrete. Okay, so DSP concrete is a ultra high performance concrete material which is designed by maximizing the particle packing density using fine particles, resulting in a very compact and low porosity microstructure. The concept is almost the same like what is there in MDF concrete. Just here there is extremely low water to cement ratio. There was less than 0.25. Here it is like it can go up till 0.18 also. There's high binder content. There is no coarse aggregate which is present in this concrete, and there is very low porosity which reduces the micro defect and the capillary pores, and strength can go up till 150 to 250 MPa also. Okay, so high strength concrete we saw it is ranges between 60 to 100 MPa. Now these concrete that we are talking about now, their strength is more than 100 MPa. Okay, and how we make this DSP concrete? By using ordinary Portland cement, silica fume at a certain replacement percent, by using very fine quartz sand so that we can minimize the presence of voids, by using certain superplasticizers so that we can make the concrete workable initially, and optional adding of fibers or polymers to enhance the property. And the last one in the UHPC concrete is the reactive powder concrete, which is designated as RPC. So again, as a matter of fact, this RPC was developed in 1990s in France as a leap beyond DSP concrete. So these are like generation after generation, some new ultra high performance concrete was developing. So RPC came after this two, MDF concrete and DSP concrete, and it is considered right now as the forerunner in the ultra high performance concrete system. Okay, so what is this RPC? So it is an ultra high performance composite developed by optimizing the particle packing, removing the coarse aggregate, and incorporating reactive powder, fiber, and superplasticizer to achieve extreme strength and durability. So there is no coarse aggregate at all. This densified matrix, which has a minimum porosity and micro cracks. This fiber reinforcement that is there inside, which enables strain hardening and ductile behavior. And this high packing density, which like of engineered ceramics. Okay, so for other two, we saw that these fibers and fine quartz and they were not necessary, but now for RPC concrete they have become necessary. So we have binder composition, which consists of OPC and silica fume and a very low WIC ratio. So for DSP concrete, we saw this ranges between 0.18 to 0.25, but here it is lower than zero point 0.2. Okay, for reactive powder concrete, we uses very fine quartz sand and ground quartz powder as aggregate system. Super plasticizer a must, high performance super plasticizer water reducer. And now here fibers also become an essential thing, like steel fiber or PVA fiber becomes very essential part of a reactive powder concrete. So since we have talked about all these three categories of UHPC, let's see how they compare to each other. So first, the basic idea in all are the same, to make the concrete denser. However, if we talk about different key features of on which these three categories of UHPC can be compared, so in terms of origin, MDF came first, then DSP came, and then RPC came. The main concept in MDF is eliminating the micro defect, while in DSP it is maximizing the particle packing, and in RPC it is maximizing the performance by both reactivity and packing. Water to cement ratio, it is generally 0.25 in case of MDF concrete. It ranges from 0.18 to 0.25 in DSP concrete, while it is lower than zero point 0.2 in RPC concrete. Aggregate used, here we use fine sand with no coarse aggregate. Here we use fine quartz sand, and here we use no coarse aggregate, very ultra fine quartz is used as aggregate. Silica fume is common in all the three cases, which is used as a mineral admixture. However, in DSP concrete, we are also using quartz powder, while in RPC concrete, we are using ground quartz and other mineral additive also to make the concrete. Fibers are optional in case of MDF and DSP concrete, but they become an essential part in RPC concrete. So you can see in terms of strength, the strength of MDF concrete will be in the range of 100 to 150 MPa. Then by making concrete denser, by densifying the concrete further, we go up till 150 to 250 MPa in DSP concrete. And finally, by further densifying the concrete by using very ultra fine quartz and reactive mineral admixture and fibers, we can increase the strength maybe up to 800 MPa also in case of RPC concrete. Okay, so now based on these the things that we have learned from high strength concrete and ultra high performance concrete, just try to answer these three questions first. And in the meantime, if anyone has any doubt regarding this part, they can ask. Okay, so what will be the answer for the first question? Can anyone tell me? Which of the following is the most likely reason for increased autogeneous shrinkage in high strength concrete and ultra high performance concrete? So we saw autogeneous shrinkage. It is due to the chemical reaction between the cement and the water, which leads to decrease in the volume of the hydration product compared to unhydrated product. Okay, so this question is very simple. Yes, the correct answer will be C. Use of flow water to binder ratio. Okay, so this we have already discussed just couple of slides back. Question number two: what is the primary function of polypropylene fiber or any kind of fiber in UHPC and high strength concrete under fire conditions? Suppose my concrete, high strength concrete or ultra high performance concrete is subjected to fire conditions, and I'm using fiber. So, what fiber? How fiber can help? We'll later on discuss about fibers further also, but just try to think. There is a limitation with high strength concrete, that is the fiber fire resistance. How fibers can improve that? Does anyone know the answer? So in fire conditions, what is happening? The moisture is inside, trapped inside the concrete. The moisture that is converted into steam, it is trapped inside the concrete and it is not able to escape because of very low porosity in the concrete. How fibers will help in that? Can anyone else try to answer? Okay, so the correct answer for this is C. Okay, the what fiber is doing, it is providing channel for vapor escape. How? So what happens? This polypropylene fiber, they melts at a very low temperature, maybe around 160 degrees Celsius. And when they melt, they leave a tiny channel behind that can release the pressure that is building up inside the concrete. And this reduces the risk of explosive spalling of concrete due to entrapped gases. Okay, and this becomes a very crucial feature for a fire resistance high strength concrete. So that's why it is specially mentioned polypropylene fiber. They have a very low melting point. So they melt even at a temperature of 160 degrees Celsius. And when they will melt, they will create the channel for vapor release. Okay, so that is how we can improve the fire resistance property. Question number three: which curing method is often recommended in achieving ultra high strength in reactive powder concrete? Okay, so initially we talked that the curing can also be a key feature in certain special purpose concrete. So how curing will be a key feature for reactive powder concrete? Okay, so since I have not taught this, I will just explain you the concept. I didn't cover these two questions in the theory. Why? Because so that I can cover them in the questionnaire part. Okay, so in reactive powder concrete or in general any type of ultra high performance concrete, uh, these concrete they achieve maximum potential when they are cured under steam at a elevated temperature. Okay, that can be up to 90 degrees Celsius. Why? Because under elevated can temperature, as the temperature increases, the kinetics of the reaction increases. As the kinetics of the reaction will increase, it will accelerate the pozzolanic reaction and the hydration of cement, and which will significantly enhance the mechanical properties and the density of my concrete. Okay, so since we are using supplementary cementitious material, they can be slow to react. So if we are using steam curing, they it will increase the reactivity of those SCMs, and we can may have a higher strength gain initially also. Okay, now try to answer these three more questions. They are mostly related to the ultra high performance concrete thing. So question number four: what distinguishes ultra high performance concrete from high strength concrete in terms of mechanical behavior? So can anyone tell me the answer for question number four? Okay, so for question number 4, the answer will be D. How, I will tell you. So, if you remember when we talked about high strength concrete and we saw the stress strain behavior, so what was happening? It was showing a brittle failure. So, though the strength was high, but it will fail in a brittle manner. It was not showing sufficient strain beyond peak load. But in ultra high performance concrete, especially the one which uses fibers, it shows strain hardening behavior in tension. So your strain will be like this. It will go like this and then it will fail and it will come down. Okay. So this means that in it can carry increasing tensile load after cracking, okay, which exhibits a ductile response rather than a brittle response that was coming in high strength concrete. Okay, so this is how ultra high performance concrete can differ in from high strength concrete. Okay, especially when we use fiber. So this part we'll see again later on when we'll talk about fiber reinforced concrete. In UHPC mixture design, the absence of coarse aggregate primarily contributes to what? So this is a very simple question. Can anyone tell me the answer? Okay, so this is a very simple question that I don't need to discuss anymore. So by removing the coarse aggregate, UHPC avoids the ITZ between cement paste and the aggregate. And this ITZ we have understood from previous session. These are the weak points that are there inside the concrete. Okay, so that's why eliminating the weak interfacial transition zone is done by the absence of coarse aggregate. Question number 6, in UHPC, the suppression of calcium hydroxide in the hydrated matrix is advantageous because. So why this absence of calcium hydroxide is advantageous in UHPC? Can you tell me the answer? Okay, anyone else try to answer? Okay, yes, the correct answer is C. Why? Because we have read earlier when we talked about durability of concrete. Calcium hydroxide is a relatively soluble and vulnerable to chemical attacks like carbonation or sulfate attack and all. So in UHPC, what happens? This suppression of calcium hydroxide due to pozzolanic reaction with silica fume, it makes concrete denser, more durable with fewer weak zones. So this calcium hydroxide again, like coarse aggregate, it is also weak zone in concrete. So if we eliminate this, we can make a enhance the durability of the concrete. Okay, so let's move ahead. Now the next category in special purpose concrete is self compacting concrete. So, as the name suggests, this concrete is also known as self-consolidating concrete, and it is a highly flowable, non-segregating concrete that can spread into space and fill formwork completely under its own weight without the need of any mechanical vibration. Okay, so it is highly flowable, it is not segregating, and it is spreading on its own, and there is no need of chemical vibration. So that defines a self compacting concrete. So just to give you an idea of how this self compacting concrete came, so it was developed in Japan way back in 1980s to address labor shortages and durability concern of concrete structure, especially in a complex congested reinforcement area. Okay, so for to address this issue of labor shortage and durability concern, self-compacting concrete was developed. Okay. Now, what are the characteristics of self-compacting concrete that makes it special? So it is the high flowability. So it can easily flow through formwork around obstacles like rebar without need of any compaction, and it has a slump typically between 650 to 800 mm, which is much higher than the conventional concrete. Passing ability, it can pass through denser reinforcement without blocking, and this is achieved by with admixture and optimized aggregate gradation. Segregation resistance, even after having such high flowability, it is cohesive enough to avoid separation of aggregate from the cement paste. So even though there is such a high flowability, there is no bleeding in the concrete, and it is self-leveling. So naturally, it can level once it is poured. There is no need of any compacting force that is required, and due to these four key properties, it makes it a special purpose concrete. So in this image, one can see how a SCC concrete mixture appears. So we can easily see that it's a highly flowable mixture from the first image. Okay, and there is nothing like segregation or building which is visible once after it gets poured. And in the second image, we can see how freely it is flowing through between the reinforcement spaces, and it is trying to level under its own weight under the effect of gravity without the need of any compaction energy. Okay, so these are the key properties of self-compacting concrete. And what are the ingredients in concrete that help that is used for designing a self-compacting concrete? So first is a super plasticizer. So we need a very high range super plasticizer which can enhance the flow without adding additional water. Like polycarbolates are the third gen super plasticizer which can be used. Then we need a viscosity modifying agent which can improve the segregation resistance. So it will bring in the cohesiveness to the system. Okay, even after having such a high flow, my concrete should be cohesive, and that is done by adding viscosity modifying admixture which improves the segregation resistance of the concrete. Then aggregate proportion, so the size of coarse aggregate here is limited up to sometimes within 10 mm also, while the proportion is around 28 to 35% by the volume of total aggregate. So decreasing the coarse aggregate helps us to make a cohesive mix and a flowable mix, and fire aggregate content is higher, like 40 to 55% of the total aggregate volume. And water to cement ratio, so it can range between zero point 0.8 to 1.1 based on the required strength and the workability demand. So it has generally it has more W by C ratio than conventional concrete. The reason is simple: we need to make concrete highly flowable. So in this figure you can see how it is changing. Self-compacting concrete is differ from conventional concrete. So the air void water may increase. Okay, it may remain the same, it may increase. The cement content is now more because it is now cement plus fine powder thing which is also present. The sand content is almost the same, but the coarse aggregate content now it is decreasing to make a self-consolidating concrete. Now, how these ingredients are engineered to form a self-compacting concrete. So, the following flowchart just presents a short overview on the process. So, for first, we start with the aggregate. So, packing density of aggregate is optimized first. Now, once we know the amount of voids after optimizing the packing density, the best proportion of cement and powder is determined using Plumke test for the packing density. And the paste volume, we know it is the void volume plus the required slump minus 321 by 4. So this formula of achieving a self-compacting concrete was derived by IIT Madras. So this formula you see here, this was derived by IIT Madras to design a self-compacting concrete. Okay, so they say that the paste volume that you are taking, it should be sufficient enough to fill the voids that are left even after optimized packing, plus the additional paste that are required for achieving a self-compacting concrete. Okay, so this is how they got the paste volume, and after determining the composition, proportion of cement and powder that needs to be used. Okay. Once the paste volume is determined, SP dosage is optimized using mini slump test. Okay, so that there is a high spread and no bleeding. Okay, and this is important to achieve the high workability. And we add viscosity modifier dosage again is also optimized using marble test. march cone test we can say, or marble test. Using marble test we optimize the viscosity of the concrete so that there is no segregation in, even after such high slump value. And finally, when we talk about all this flowability, passing ability, and cohesive property of SCC, how do we test a SCC mixture quality? Suppose you have prepared a self-compacting concrete. Now, how you will test for different properties of self-compacting concrete? So, generally, there are four tests, 4 to 5 tests. There is also U-box test. Okay, so there is U-box test, there is slump flow test, which is used to check the flowability and the spread diameter. There is G-ring test, which is used to check the passing ability through rebar. There is L-box test, which is again used to check the passing and the blocking ratio. And there is V-funnel test, which is used to check the flow time and the viscosity of my concrete. Okay, so you can see in these images. So this is a U box setup. This is a slump cone slump test. There is a L box setup and there is a V funnel setup. And this is how a G ring test looks like. So in the middle we pour the concrete and then we allow the concrete to spread. So this reinforcement, they should not become an obstacle for concrete to spread. Okay, that is a demand for a self-compacting concrete. It should be freely flowable between the reinforcement. So in U-box test, like we saw here, figure 1 shows how the testing is performed. So you can see on one side concrete is filled and the central gate is closed. Okay, this gate comprises of different spacing. Okay, so once the gate is opened, the concrete try to flow through this gate and the spacing between them, and as the concrete is allowed to pass through the gate, it will fill the other side of the box, and the height of fill is what is of the interest to us. Okay, so you can see from here the concrete fills here. So if the height of fill is very low, then we say it is has a very low flowability. So it is a very stiff mix for in terms of SCC. If the height is comparable, then we say that the concrete is good enough. It is okay for SCC. And if there is again height is low, then instead of flowability there can be issue of the segregation also that is happening. So you may see all the water coming up here and the cement paste here. So that can show you whether there is too much flowability of the we have added SP beyond a limit, which has led to bleeding, or if there is no enough viscosity modifying admixture to keep the concrete cohesive. So using this test we can have that judgment. Then slump flow test we have already discussed earlier, so we will just spread the concrete mix and we'll record the diameter. Here we don't record the loss in height, okay, because it will completely flow and collapse, so we record the diameter. So as per IS 456, the criteria to satisfy SCC by slump flow test should be 64 centimeter to 75 centimeter, or 640 mm to 750 mm. Okay, then there is V funnel test, which is used to check the time taken by concrete to flow through a very confined opening. So the criteria to satisfy by SCC is time should be in the between 10 plus minus 3 seconds. Okay, so to till a certain height, concrete is filled here, and then this nozzle is opened and the concrete is allowed to freely fall from the nozzle, and the time is recorded how much time the concrete is taking to pass. Okay, then in L box text again, same as U box test, we have filled the concrete here. There is a door here and there are channels here, reinforcement challenge, which is acting as a blocking rod. Once the gate is opened, the concrete will try to flow through this channel. Okay, and the difference in the height, like this is my initial height H1, okay, and this is my final height H2. So the ratio of this will determine the passing ability of the concrete, or this it will help us to comment on the segregation or bleeding if there is in our concrete. So the criteria to satisfy SCC is that this H2 by H1 should be at least 0.8. Okay, so it should be like this, not like this. Okay, so till here maybe the SCC should be able to fill. Okay, if it is filling to a very low depth, that means that either there is bleeding that is happening, or through reinforcement, my aggregates, my concrete is not able to pass, or it is very stiff, or like we have added too much of viscosity modifying admixture, that can also result in lower H2 by H1 ratio. And apart from the conventional testing, there is one more testing in the name of sieve segregation testing, which is used to check the segregation of bleeding in self-compacting concrete. So how this test is performed, we can see in both figure and flow chart. So you can see in the figure, first concrete is filled inside a cylinder, and the concrete is allowed to stand in that bucket or a cylinder for 15 minutes. Now after 15 minutes, we'll pour 2 liters of concrete, the top 2 liters of concrete on the sieve with an opening of 4.75 mm as per IS 456, and there is a pan at the bottom. Okay. Now, as we'll pour the concrete on the sieve, what will happen if there will be fine component which can pass through 4.75, they will pass and they will fill the pan, and the remaining will remain at the top of the 4.75 mm sieve. And then we'll record the ratio of mass passing to the total mass poured, and it will denote it as the segregation resistance. So mass passing, so out of suppose 100 gram, if there is only 10 gram that is retained at the top of 4.75 mmc, so 90 gram is the mass passing, and the total poured mass is 100 grams. So this ratio will become equal to zero point 0.9 or 90%, we can say. Okay, so if the value is between 5 to 15%, the segregation resistance, then we say it is good, like it is satisfactory. If it is low than 5%, then we say there is a very high resistance that the concrete is offering, and if it is greater than 15%, then we say that there is possibility of segregation that may have happened. Okay, so this is also one of the common tests which is used to judge SCC. Now try to answer these questions based on self-compacting concrete. In the meantime, if you have any doubt, you can ask. Field application, you can see in case of highly reinforced system where the spacing between the reinforcement is very small, or where the design of formwork or the structure is very complicated. Like suppose if I show you by a drawing. Okay, suppose you have a like a section of concrete like this. Okay, and there's heavy reinforcement that is present. Okay, now what will happen if you will pour on the conventional concrete which has aggregates up to 20 mm, the space between the reinforcement may not be even 20 mm. And if you are pouring concrete such like this conventional concrete, what will happen, my concrete may not be easily able to flow through the spacing between the reinforcement. It may not reach all the confined area properly. And suppose if my formwork is a little complicated, not simple, so what will happen if my concrete is not highly flowable, it may reach up till here, it may reach up till here, but here the concrete may not even reach. So just to have a concrete which can easily flow through congested spaces and cover each and every corner, we use self-compacting concrete. So it has a property, it can flow under its own weight. We don't need to apply any compaction. So under its own weight, it will flow and cover all the spaces, and it won't be blocked by any of such reinforcements or confinements that are there inside the concrete. For dams, you can use, but dams are like high mass concreting things. There, I don't think so. We need very high reinforcement volume inside concrete. For dams and pavements, we use roller compacted concrete. We'll see why. Okay, because it is also about the heat of hydration that the system is generating. Here you can see there will be higher volume of cement paste that is there in the system, which can generate a lot of heat of hydration. Okay, so we need to take care about that also. The quantity of concreting that we are doing, that also matters. In dams in general, there is not that high load demand that we need. Okay, so their reinforcement spacing, it is far away compared to what is there in congested system. Okay, can anyone tell me the question of answer of question number 7? If a self-compacting concrete mix shows a high T50 time, okay, like slow spread to 500 mm in slump flow test, what is the probable issue? Okay, so this T 500 times means the time taken by the concrete to spread to 500 mm slump. Okay, what can be the issue if it shows a very high, it takes more time to spread? Okay, so correct answer is C, as you answered, one of you answered. Why? Because this T 500 time will reflect the flow rate, the rate at which the flow is happening. And if it is high, it means my concrete is sluggish in nature due to its viscous nature. So if my concrete has high viscosity, it will flow at a slower rate. So that's why answer is high viscosity and yield stress. Question number 8. The potential of dynamic segregation in self-compacting concrete during pumping or placement is most influenced by. So suppose there is segregation that is happening in self-compacting concrete during pumping or placement. What can be the key reason behind that? Or how we can influence that segregation? How we can improve that segregation? Can anyone tell the answer of core question number 8? Okay, so it is the plastic viscosity. Okay, which will be the critical factor. Okay, so when I talk about high plastic viscosity will help me to resist segregation during movement of concrete. Okay, so if my concrete is viscous enough, then it will be cohesive also, which will help my concrete to not segregate. Okay, question number 9. SCC mix shows excellent flow but fails L box on G ring test. The most likely indication is, so it is flowing but it is not passing L box or G ring test. What can be the most likely indication to this? Okay, so as the question itself has said about the answer, it is the correct answer is adequate flowability but poor passing ability. So you see, it has an excellent flow, so it means it has adequate flowability that is needed, but it is failing to fails the L box or G ring test. So as we saw earlier here, if anyone remembers, this is a G-ring test which talks about passing ability, and the L-box test also talks about the passing ability. So though the concrete is flowable, it is failing. It has a poor passing ability. Why? It can happen due to insufficient segregation resistance. The concrete is flowing, but it can't navigate properly through obstructions. It maybe it is too segregated, or the there is proportion of coarse aggregate also which is dominating. Okay, which is making concrete fail L box or J ring test. Now just try to answer these questions here. So these questions are framed like how a self-compacting concrete is comparing to conventional concrete, or in terms of mechanical properties of self-compacting concrete. So that question I didn't cover in the theory, but try to answer this question. So try to remember what we have talked earlier in earlier sessions also. So question number 10, compared to conventional concrete, SCC generally shows which feature? Okay, so just now while I was addressing one of the doubts of a person, I talked about that since there is a high paste volume that is there in self-compacting concrete, it can show higher shrinkage compared to conventional concrete. Thus, its use is uh, not recommended for mass concreting purposes. Okay. Question number 11. Which of the following characteristics of self compacting concrete allows it to achieve high durability despite high flowability? So, initially, talked that it is concrete which is used in special cases, like for achieving good durability and performance also. How this high durability is coming even though it has such a high water content? Okay, so the correct answer, I guess, is B. Okay, so when we are talking about a self-compacting concrete, we have reduced the particle size of coarse aggregate. Okay, now initially we talked how self-compacting concrete is made. First step is the uh, optimizing the particle packing, and then we optimize the cement paste, and we optimize the superplacid, and we optimize the viscosity modifying agent. So what this optimization done, it improves the particle packing and it makes concrete dense. Okay, so even though after such congested reinforcement space, my concrete is able to freely flow through the openings that is there, and it is able to form a dense composition in reinforced concrete, which makes it a highly durable concrete despite having flowability. Question number 12. The modulus of elasticity of self-compacting concrete compared to conventional concrete is typically what it will be? Higher, lower, or the same? Okay, so if you remember this diagram we saw in case of high strength concrete. So I will just copy this diagram so that you can answer to this question. So if you see, the modulus of elasticity of my concrete is generally enhanced by the presence of the aggregate in the concrete. Now, in self-compacting concrete, there is very low proportion of aggregate. So what will happen? Eventually, this curve will also go down. So the correct answer is lower due to reduced coarse aggregate content. Okay. Any doubts in the portion that we have discussed till now? High strength concrete, ultra high performance concrete, and self-compacting concrete. So these three are the most famous special purpose concrete. Now everything that we are discussing from now for ahead, they are special purpose concrete, but they are not used very commonly. So their application now will be very specific or very limited. Okay. So till here, whatever we talk, these are the major special purpose concrete.
Sir, one doubt.
Yes.
Sir, when you are going for producing the self-compacting concrete,
Yes.
so if you use powder content with replacing the cement,
Yes.
so like if you are going for replacing the cement with a 10, like 5, 10, 15, 20, 25 like that, so then water demand will be increases by the powder content. Then how to manage that water cement ratio?
See, when we are talking about the self-compacting concrete, the strength may not be that concern for us. Okay. And again, to manage the water to cement ratio, we have super plasticizers that are there in the system. Okay. So if I am increasing the cement content, the powder cement, everything, C plus P, in the similar way, I can increase the water content also. Okay. So W by C ratio may remain the same, okay, for us, but to achieve that high flowability of the system, we have the super plasticizer which we are optimizing.
Sir, means
And
for higher percentage replacement, we have to decide the water cement ratio or what?
what?
So for higher percentage replacement with the cement, we have to fix the water cement ratio or how to decide the water cement ratio.
See, water to
So
cement
means,
ratio is the property of strength of my concrete. Okay, more is the water in the cement, more it will be the workability of my concrete. So generally you see water to cement ratio for self compacting concrete, it is relatively high compared to conventional concrete. Okay, so its strength will be lower compared to conventional concrete, but for us the important thing is the compaction that is happening in the concrete. Okay, so this, as the cement paste content is increasing, the water content is increasing, and the but the W by C ratio, okay, it will remain in this range. Okay, and that will give us that cohesiveness, the flowability, all the things together.
So what kind of admixture can you use for this SCC then?
Very high range water reducing admixture, third gen, fourth gen super plasticizers. So if you go back to the discussion that we had earlier, there is normal range water reducers and there is high range water reducers. So that high range water reducers we can use when we are talking about SCC, because they can increase the flowability at a lower dosage also. At like suppose I'm adding 1% of superpluses, that will provide more uh, deconvolution of my cement particles, okay, which will increase the flowability. So we use high range water reducing admixtures in
Is
terms.
there any specific kind of super pulsar in
There
high
are
range water
lot of
reducing?
there which are present in market. There is third gen, so polycarboxylate based superplasticizers. So generally we use this PC type, third gen PC we say we use, and there are much more. So there, that detail you can see. There are different generations of superplasticizer: first generation, second generation, third generation, fourth generation. So generally this third generation and fourth generation we use, we say that these are high range water reducing admixtures.
Okay, sir. Thank you.
Anyone else was saying in the background? I heard someone. Any other doubt? Okay, I don't see any question. Okay, so let's move ahead now. And the next one in the special purpose concrete that we will talk is the fiber reinforced concrete. Okay, so if we look at how the use of fiber in concrete came into existence, so this concept came from mixing mud and straw, which dates back in ancient time in Egypt, where fiber was used to prevent cracking and shrinkage during drying. So this ancient knowledge laid the foundation of modern fiber reinforced concrete. So initially it started with the use of mud and straw as fibers to prevent cracking, and now it has come to a special category of concrete as fiber reinforced concrete, where discrete fibers are added in concrete to improve the performance, especially in terms of tensile strength, toughness, and the crack resistance. Okay. Now, when we talk about fiber in concreting, some of the common types of fiber that are used are steel fiber, glass fiber, synthetic fiber, and natural fiber. So, which fiber to use depends upon the application need and the specific fiber property that that is there. So steel fiber, it enhances the toughness and the impact resistance. The glass fiber, it is used for lightweight application. Synthetic fibers, it reduces the plastic shrinkage, while natural fibers, it is low cost and sustainable. So based on the application demand, the choice of fiber material can change. Now, what is the role of fiber in fiber reinforced concrete? The same uh, we can understand from this figure. Okay, so fiber is used that we used in FRC. They are short, randomly oriented, and uniformly distributed fibers, and they act as crack arrestor bridge, which bridges the micro crack and improve the ductility. So you can see here my concrete is trying to spread away, but the fibers that are present in, which is starting from here and going till here, it is trying to resist my concrete from failing. So it is trying to arrest the crack that is there in the concrete under loading, which is bridging the micro cracks and which is improving the durability of my concrete. Okay, so now it is not just about the fiber material that we talked here, it is also about the orientation of fiber which can become important. So if there is vertical fiber, so if my concrete is like this, load is applied in this direction and I have a vertical fiber, fibers are oriented like this. So if all fibers are aligned vertically, only the vertical component of fiber stress contributes in resisting the load. Okay, so this vertical component of my fiber, it will contribute in resisting the load. If the fibers are horizontal, then the contribution is maximized in the direction of the fiber alignment. Okay, so if from these 2 points we can understand the direction in which the fiber is aligned, in that direction the property of concrete is enhanced. Okay, and random orientation will be like in real fiber reinforced concrete, the fibers are randomly oriented in 3D, so it is very difficult to orient fiber in a particular direction, rather it is random orientation in 3D. So there is average effectiveness which is derived by integrating all possible angles. So suppose my fiber is oriented along this side, and the strength is sigma, stress is sigma, and this angle is theta from horizontal. So when I am talking about the vertical loading condition, then the phi sine theta, the sigma sine theta component of the fiber will contribute in resisting the load. Okay, so this is why it is said average effectiveness is derived by integrating all possible angle. So this fiber is oriented like this, some will be oriented like this, some will be like this, some will be like this, some will be like this. So in this way we can generate the vertical component of each fiber, and we can know the effectiveness of fiber that is coming. Okay, now if we try to understand this orientation thing further, so when fibers are orientated along the direction of loading, we say the system is unidirectionally composite longitudinally stress system. Okay, so suppose this is my concrete which is matrix. Okay, and this fiber, so I have made a single fiber throughout the length of concrete. I like fiber will be not this big, it will be small pieces. So suppose they are aligned in a straight line and either a single fiber throughout the length. So what will happen under this loading, this matrix and this fiber will experience the same strain. Okay, so my concrete under this loading will experience a, this will be psi L. So the strain in concrete under this longitudinal loading will be equal to strain in fiber, which will be equal to the strain in the matrix. Okay, so the load taken by this fiber reinforced concrete, it will be nothing but the load taken by the fibers plus the load taken by the matrix, which is my concrete. Okay, now load we can write as stress into area. Okay, and stress we can write as elastic modulus times the strain value. So the same this calculation I have performed and I have written this equation here. Okay, so first I have written load as stress into area, and then stress I have written as elastic modulus times the strain. Okay, now since the strain is same in all the three component, it will cancel out. So the net modulus of elasticity of my concrete, it will be like denoted by the elastic modulus of fibers times the volume fraction of fiber plus elastic modulus of matrix times the volume fraction of matrix. How this volume fraction thing came? If I will divide this AC area on both the side, so AF upon AC. Okay, now since it is uniform, the length of fiber and the concrete is the same, so if I will multiply this by L, so it will give me VF upon VC, and this VF upon VC is nothing but the volume fraction of fiber in the system. So you can see along the direction of loading how the elasticity modulus is enhanced by the fiber. Okay, and as the elasticity modulus is enhanced, the stress taken by the concrete component in longitudinal direction will also be enhanced, and it will be directly proportional to the volume fraction of fiber in the system. Now, the same thing when the fiber is oriented perpendicular to the direction of load. So suppose this is my concrete cube and my fiber is oriented in along this direction and the loading is happening along this direction. So the such system is known as unidirectional composite transversely stress system. So in this, what will happen? Now the strain is not the same in both matrix and fiber, but the stress is the same in both matrix and fiber. So the stress of concrete in transverse direction is the same as the stress in fibers, which is equal to the stress in matrix. Okay, so the total transverse displacement now will be the displacement of concrete times the displacement of plus the displacement of fiber. Okay, so you can write strain as the sum of length change of fiber plus matrix. Okay, and strain we can write in terms of stress upon elasticity modulus. Okay, so when you write strain in terms of elasticity modulus, okay, and volume fraction will come from here. You can see TF upon TF we are doing. So strain we are converting into the change in length we are converting into strain, and since the area is the same, okay, so I can write it as volume fraction also. This TF upon TC, I can write as volume fraction. So it will become VF and it will become VM. So you can see here in transverse direction, the addition of fiber, it will contribute to a inverse relation in increasing the elasticity modulus of concrete. While in longitudinal direction, it was contributing as a direct relation. So this relationship is also known as rule of matrix. Okay, if you want to remember it in a easy way, it is known as rule of matrix. Okay, so that is why we say when the fiber is oriented along the longitudinal direction, they will have the maximum contribution in resisting the load. Okay, there are further calculation, there are further theory that were taught in the live session in the NPTEL course also, but I have restricted them in this part of discussion because that was all about the back end, how fiber is cracking, how that crack is contributing to the load. That everything we'll see in the theory in terms of theory. This was important because it will help you to understand how the orientation is affecting the behavior of fiber. So I've just kept this orientation part in my presentation. Now, often when we talk about use of fiber in concrete, we are confused in two terminologies. There is fiber reinforced concrete and there is fiber reinforced polymer concrete. So, just to clarify over depth that FRC enhances the intrinsic property of concrete matrix, whereas FRP is the reinforcing material which is used externally or internally. So you can see this is FRC. So this fiber we are adding inside the concrete during concreting. Okay, while FRP is a wrapping, it is a material which is applied outside the concrete once the concrete is hardened. Okay, so both has different application. So if we check in terms of the different properties, you can see FRC, it affects the cement. Okay, it is a cement based system, fiber reinforced concrete, while FRP is a polymer based system. Okay, so this material, it is stick with concrete with using a polymer, where FRC we have the cement paste and which is acting as the matrix. Here polymer is acting as the matrix. And what is the role of fiber? It is enhancing the concrete matrix. So you can see here, it has enhanced the modulus of elasticity of concrete. While in FRP, the concrete is not enhanced, but the ultimate load bearing capacity of concrete has enhanced. Fiber orientation, here it is random or partially aligned. However, in this FRP thing, it is usually unidirectional. Okay, so in the direction of which we want to enhance the property, in that direction only we wrap the FRP sheets. Where it is used to increase the toughness or for making crack control, while FRP it is used for retrofitting and repair application. And it is applied, it is mixed with concrete. Here fiber is mixed with concrete, while here fibers is used as bar sheets and laminate over the cover. Okay, so this is how both FRP and FRC differ from each other. Now, if we come back to fiber reinforced concrete and see how stress versus strain relationship will look like under loading. So, compared to conventional concrete, which will fail drastically after peak load, use of low volume or high volume fiber has two positive effects. First is the increment in the ultimate load capacity from here till here. And so you can see in case of FRC with high volume of fibers, it has a higher ultimate load capacity because there is a high volume fraction of fiber which is contributing and taking more stress. While low volume fiber, it is contributing less contribution of fiber and stress, so there is less increase in the stress of concrete. And second is the behavior post peak. So you can see conventional concrete, it can show sudden failure post peak. However, fiber reinforced concrete, it will show strain softening behavior. So you can see it is strain is decreasing gradually over time and then failure will happen. Okay, and this will increase the net strain taken by the concrete before failure. Okay, so you can see in the FRP also there is strain hardening phase and then there is strain softening phase and then there is cracking. So it is taking more strain before failure. So it is increasing the toughness of my concrete. Okay, so, as written in these 3 points also, so it shows post-cracking ductile behavior when I use FRP. It bridges the crack which shows strain hardening or softening depending upon the fiber type and volume, and it increases the energy absorption capacity, which is nothing but the area under the stress strain curve. So this area will be comparatively low compared to when the area which is there in the fiber reinforced concrete with high volume. Now it is not just about the volume of fiber which is important, but it is also about the property, the size and the shape of fiber, which becomes important in dictating the property of an FRC. Okay. So if you talk in terms of shape, there are straight fiber which are easy to mix, but they have weaker bond and may pull out easily. While there is crimped or wavy fiber which has better grip with concrete, which improves the bonding, and twisted and indented fiber, they enhances the friction and the pull resistance ability. So this is the effect of shape of fiber. Effect of size. So when we talk about size, we talk about aspect ratio, the length to diameter. So length of fiber to the diameter of fiber. It is a key property when we talk about a fiber reinforced concrete. So if there is a higher aspect ratio, we say there is higher crack bridging. Okay. However, too high can reduce the workability and cross clumping. Okay. So shorter fiber, they are good for shrinkage control, while longer fiber, they are used in load bearing and structural application. Okay. Then material properties or tensile strength. So higher is the strength of fiber, better is the load carrying capacity, because we have seen the role of mixture. Sigma CL is equal to VF times sigma F. Okay, so this is directly proportional to the stress taken by the fiber also, plus Vm times sigma M. Okay, so we can see from here these two characteristics. So higher tensile strength means there will be more load carrying capacity, higher modulus of elasticity, it increases the crack control efficiency, and if the modulus of elasticity is low, it is good for plastic shrinkage and not for structural application, and bond with matrix. So if you have a rough texture or a crimping or a coating fiber, it will enhance the, it will affect the bonding with the matrix also. So this is how material property of fiber can affect the performance of a FRC. And finally, how fiber reinforced concrete behaves at different stages post concreting. So you can see fiber reduces the workability. Why? Because we are adding some stiffness to the concrete mix. Okay, especially when we are using high volume fiber. So use of super plasticizer becomes a must in case of fiber reinforced concrete. Strength, compressor strength may not change significantly, or it can change because there are fibers which are bridging. Okay, if in low fiber volume it may not change significantly, but in high fiber volume it can change. However, tensile strength and flexure strength improves significantly because crack is getting arrested now, and the crack resistance increases even under cyclic or impact loading. So that this part we have already seen in the stress strain relationship. And durability, fiber can improve the freeze thaw cycle resistance, impact or abrasion resistance, and the plastic shrinkage cracking. Okay, so these we can commonly understand because they are bridging the cracking. However, if we are using steel fiber, they may corrode if they are exposed to severe exposure condition. So we need to take care of that. So instead of that, natural synthetic fiber can be preferred for corrosion resistance. Okay, so this was all about fiber reinforced concrete. Anyone has any doubt in this part about fiber reinforced concrete? We'll see the question shortly after roller compacted concrete. Any doubt in this part? I will like pause for a minute and then I will come back again. If you have any doubt, you can ask your doubt right now. If anyone has any doubt, they can post their query right now. I will be back in a minute. I will start the session again in a minute. Okay, since there no doubt, will continue. Okay. Now after FRC, we have roller compacted concrete. Okay, so what is roller compacted concrete? It is a very dry concrete mix with zero slump consistency, which can be compacted using roller. Okay, and uses the same basic ingredients at conventional concrete, but it has a very low water to cementation, a high amount of fine aggregate to maintain workability in a dry mix. So here cement act as a binder, water is very limited, just enough to for hydration. Aggregates we are using both coarse and fine aggregate, and admixture is optional. We can use fly ash, slag, water reducer to enhance the performance. Now, because of this low water content, what happens? This roller compacted concrete, it has zero slump, meaning that it doesn't flow like normal concrete. It is like a damp soil. Okay, and what are this? What are the key features of this concrete? It is the dry consistency, which allows compaction by a roller. So for compacting this concrete, we use vibrating rollers. It has a fast placement and minimum formwork need, since it has very low slump. So formwork need is minimum, and it can be placed fast. It has high strength and durability, especially for heavy load applications, since it has a very low water to cement ratio, and it is low cost because it has because of the reduced cement demand and quicker construction time. Okay, so since we are not using any foam work, though there is low cost, the foam work cost is eliminated. Okay, in roller compacted concrete. So if you see how a roller compacted concrete looks like, so in the first image you can see concrete is dry enough, okay, to avoid any sinking. uh, okay, under vibrate when we perform some vibratory roller application, but it is also wet enough to allow sufficient distribution of binder mortar in concrete during mixing and vibration application. Okay, so it is not very dry, not very wet. Okay, the same can be understood from this diagram also. Okay, where you can see concrete seems dry enough, but it has still enough wetness for proper compaction. Okay, so the same is written here. It is needed to be dry enough to avoid sinking, but wet enough to avoid sufficient distribution of binder motor. Okay. Then the third and the fourth image shows the application of roller compacted concrete. This is where it is used in bridging, building dams. And here you can see it is used for building pavement. So rollers are used for compaction purpose. So these two are like the most common application of roller compacted concrete in mass construction activities. Now, just try to answer these three questions. So, these three are based on fiber reinforced concrete. And then we'll see some questions on roller compacted concrete. And in the meantime, if you have any doubts regarding roller compacted concrete, you can ask. Okay. So, can anyone tell me the answer for question number 13 if there are no doubts? Which of the following best explains the high aspect ratio fibers in FRC may reduce the overall concrete performance? Okay, so the correct answer is yes, D. Okay, so what happens when we are using high aspect ratio fiber? That means we are using a very long and a thin fiber. So what happens? There can be entanglement in between fiber, which can happen, which will lead to poor dispersion of fiber, and this can affect the workability, and it can result in a non-uniform matrix. So that is the problem with having high aspect ratio fiber. Second question, modulus of elasticity of fiber in FRC affects which property? Again, yes, the correct answer is C. So it is not the strength of concrete that is enhanced. The concrete has the same strength. But what fiber is doing? Fiber is resisting the deformation, and it is carrying load after cracking of concrete. So it helps to bridge the crack and control the crack width. especially under tensile and flexure loading. So that's why the correct answer is crack with control and load transfer efficiency, and that is due to the modulus elasticity that the fiber is incorporating. What happens when fiber content in FRC exceeds the optimal volume? So suppose there is an optimum volume. What will happen if I will go beyond that volume? Okay, so yes, the correct answer is B. So as we have talked earlier, that fiber affects the workability because it is a stiffer component that is there in the concrete. So exceeding an optimal volume, what will happen without using any adjustment like adding superelasticity, it will reduce the workability and it will make the mixing difficult, and this can lead to non-uniform dispersion of fiber and can degrade the performance of concrete. Okay. Now, try to answer these questions related to uh, roller compacted concrete. Which of the following is the primary reason RCC is not suitable for high reinforcement structure, highly reinforced concrete structure? So, one of you asked me doubt why we are not using this self-compacting concrete in bridging, in making, like why we are not using for dams and all, and why, so similarly why we don't use roller compacted concrete for high reinforced concrete structure, what can be the reason? Okay, so yes, the correct answer is C. So when we talk about RCC, it has a very low workability. If the workability is low, what will happen in highly reinforced system? My concrete will lack the enough flowability that is needed to properly flow across the dense reinforcement placing. Hence, it is not ideal for reinforced concrete members. Now, 17 question in RCC dam construction, which is the most critical factor in ensuring that there is interlayer bonding, so between different layers, what is most critical in ensuring bonding in case of reinforced roller compacted concrete? So since the concrete is very dry, there can be issue of between two pores bonding may not be proper if there is a slight delay between two pores in a in dam construction because of the dry consistency. Okay, so the correct answer for this question will be A. It is the moisture content. So that's why we are saying the mix should not be dry and not be very stiff. So for good bonding between the successive layers of roller compacted concrete, moisture content is critical. If there is a dry mix and a very dry and stiff mix, that will lead to formation of cold joint. However, if mix has certain moisture, that will be able to bind with the adjacent layer properly. Question number 18. The main reason fly ash is often used in roller compacted concrete is, so this is a very straightforward question. The answer is to reduce the heat of hydration and cost. So since we are using very low water to cement ratio, the hydration rate may be fast. Okay, and to reduce the heat of hydration, we use fly ash as an additional SCL. Okay, in roller compacted concrete. So does anyone has any doubt? No, I don't see any doubt. Okay, so let's move ahead. We have three more categories of concrete, three to four more categories of concrete left. So let's cover them fast. Now, after roller compacted concrete, we have polymer concrete composite. So these are like concrete advanced material which are made by combining polymers with traditional concrete method. And what polymer do they? They provide superior properties like high strength, rapid curing, excellent chemical resistance, and reduced permeability. Okay, so this is why we talk about polymer composite concrete. Now, in this polymer concrete composite, there are three types. There is polymer concrete where there is binder used as polymer. There is polymer cement concrete where binder is both polymer plus cement, and there is polymer impregnated concrete where polymer is impregnated in a already hardened concrete system. So how these three types of polymer concrete differ from each other? Okay, so for this, if we look at this table of how features are compared in these three types, so in polymer cement concrete, we have cement plus water plus polymer plus aggregate, which is making the PCC. And here binder is both cement and polymer. Polymer it acting as a nut filler which is reducing the porosity and increasing the strength, and it enhances the adhesion, water resistance and flexibility also. And such PCC concrete is used for thin repair and overlay like pitch repair mortar or waterproofing coating. While polymer concrete they are made of aggregates per plus polymer resin. So there is no cement here. There is 100% polymer only, and it helps in achieving high strength and chemical resistance. It has quick setting ability even at low temperature, and it is mainly used in precast industry on industrial flooring. And then there is polymer impregnated concrete, where in a hardened concrete system, low viscosity monomer is impregnated and it is polymerized by heat and radiation. So what happens? This polymerization fills the pores and it makes concrete dense and stronger. So it is mainly used for rehab and retrofitting work like bridge decks rehab, a subway rehab, parking lot rehab, and pavement rehab. Okay, so in this way, all there are three types of polymer concrete composite which differ from one another. Okay, now after polymer concrete, we have heavy concrete. Okay, so now we'll see like two special concrete which will be based on the density of concrete. Okay, so heavy concrete is like a type of concrete which is made with heavyweight aggregates instead of normal aggregate to increase the concrete density. So typically the density of such concrete can go up till 3000 kg per meter cube, whereas standard concrete has density of around only 2400 kg per meter cube. Okay, now what are the key ingredients that make heavy concrete? It is the cement, same as normal concrete, water same as normal concrete, but the concrete is made heavy because of the heavy aggregates like barite, magnetite, hematite, or steel scrap iron. So these are high density aggregates which are used to make heavy concrete, and these optional additives for workability or setting control which can be used. So what are the key properties of these heavy concrete? They have high density. As we have talked earlier, it can go up till 6000 also. Generally above 3000 can go up till 6000. They have excellent radiation shielding that we'll see in the next couple of slides. They have high compressive strength, so it is not just the aggregate which contributes to the strength, it is the cement paste also which contributes to the strength. So if these high density aggregates, that can really increase the strength of concrete also. And they have slightly more difficult to work or handle due to its weight. So that is normal because now the density of concrete is increasing, the workability may become difficult. So where are such concrete used? So you can see in case of radiation shielding, they are used because they can absorb radiation. So in this image, you can see this is my heavyweight concrete, and there are certain harmful radiation that can come in industrial buildings. So to shield those radiations from coming out, heavyweight concrete are used. So through this heavy concrete, the penetration ability of radiations like gamma rays, X-rays, and neutrons, they are very low. So that helps in radiation shielding. They are used in ballast application near offshores and pipelines. They are used as counterweights in bridges because of their high weight, and they are also used in military and security application because of their high strength and ability to absorb vibration because of their dense structure. Now, opposite to heavyweight concrete, we have lightweight concrete or low density concrete. So, lightweight concrete is designed to reduce the dead load and improve the insulation by using material of low density, and their density is typically in the range of 300 to 2000 kg per meter cube, which is much lower than the conventional concrete density. Now, to make concrete lightweight, there can be different ways in which that can be done. We can improve the aggregate from the system, which is known as pervious concrete. We can use lightweight aggregate material which can make the concrete light, or we can increase the air void inside the concrete. So using autoclave aerated concrete or foam concrete. Okay, now as you can see in the figure, as the porosity in the concrete increases, the lighter the concrete will become, and the thermal conductivity of concrete will also decrease proportionally. Okay, so this is one of the key feature of lightweight concrete, that it has lower thermal conductivity. Okay, and all these three system can bring this effect. Okay, because eventually in all the three system, either we are making the concrete lightweight or we are increasing the porosity inside the concrete. So if we just have a quick look at each of these category, so first is the lightweight aggregate concrete. So these are made with lightweight aggregates like expanded clay, shawl, pumice or perlite. So in the image you can see this concrete which is made with fly ash based aggregate or circular in nature. This image shows how lightweight aggregate looks like, and this is a instrument which is known as pelletization instrument, which is used to prepare lightweight aggregate from fly ash. So basically here what is done, fly ash is poured in this pan, and this pan is rotated at a certain angle and at a certain rpm speed, and slowly water is sprinkled. So when we spray the water, what will happen, the fly ash will agglomerate and they will form circular balls, and then the circular capsules, they are heated and dried to achieve what is known to achieve a structure of aggregate. Okay, so at the concrete that is made with such lightweight aggregate, they have a very low density. Okay, 1350 to 1850 kg per meter cube strength. They have low strength, but it is suitable for certain structural application. Okay, maybe in high rise building, okay, at top floor levels to reduce the dead weight of the structure, we use lightweight aggregate. On certain precast blocks and panel, lightweight aggregate are used, and we have already seen that fly ash can also be used for making lightweight aggregate using this process of pelletization. Another type of lightweight aggregate is by increasing the porosity in the concrete. So that is foam concrete. So you can see these are also known as aircrete or cellular concrete. And what is this? There we have cement plus water plus fine aggregate plus foaming agent. So there is a certain type of foaming agent which creates a slurry of millions of air bubbles inside the concrete. And this air bubbles results in lower density of concrete and makes concrete lightweight. So their strength is comparatively low, and they are mainly used for non-structural applications. So some of the example of foam concrete you can see here how they look like. Then there is autoclaved aerated concrete also. So these are precast factory made concrete which are lightweight in nature. They are made using aluminum powder which creates a gas bubble, and there is an autoclave for getting strength. Okay, they have low density, very low density from 400 to 800 kg per meter cube, but they are good for load bearing walls in low rise buildings, so where the strength is demand is not much. Okay, they are popularly used in making ACC blocks. So you might have heard about AAC block a lot, and they are also used for making energy efficient home high insulation because of their low thermal conductivity. And finally, the final category is in lightweight concrete is pervious concrete. So you can see this is not actually lightweight, but it is often included in lightweight because of its structure. So there is no coarse aggregate in this system. Okay, so concrete without there is no fine aggregate in the system. So without any fine aggregate, it creates high porosity in the system. Okay, because packing density of my concrete is now poor. Okay, so their density is low compared to conventional concrete, so that's why we have categorized it in lightweight concrete, and their strength is also lower compared to the regular concrete. So both the images that you see here, these are some of my project work that I carried out in IIT Indore. So in the first image, you can see how the water permeation is happening through pervious concrete paver block. And in the second image, you can see a brick which is prepared using a pervious concrete mixture proportion. So they found wide application in pavements and sidewalks, in parking lots, and in drainage and storm management area because of their ability to allow water to flow through them. Okay, now just try to answer these few questions related to polymer concrete and lightweight and heavyweight concrete, so that I you can have more clarity over the concept. So can anyone tell me the answer for question number 19? Which of the following best explain the improved mechanical performance of polymer concrete compared to traditional concrete? Okay, so as we have already discussed the role of polymer, the polymer enhances the strength. How it is enhancing the strength? Because the polymer is forming a film over the cement paste, which is enhancing the adhesion, the tensile strength, and the durability. Also, the polymer film, it can bridge the cracking inside the concrete, it can reduce the porosity, it can act as a inert filler, which can improve the mechanical properties. Now, in case of polymer impregnated concrete, polymerization is commonly initiated using which process and how? Okay, so as we have seen in the theory, I have mentioned that UV light or heat is used for polymerization. So what happens in this? Initially, my concrete is dry. Okay, then okay, so in a dry concrete, what I will do? So in a dry concrete, liquid monomer is a single unit of a polymer. So what will happen in the dry concrete? Monomer is impregnated in dry concrete. Now, once the monomer is impregnated, the polymerization is done. So this monomer chain will connect to one another and it will polymerize in a bigger chain. So that is done using UV light or heat. Okay, and this causes monomer to harden into a polymer within the concrete pore. And since this hardening or polymerization is happening inside the pore, it will fill the pores, it will increase the density of concrete and it will increase the strength and the durability of concrete. Okay, so from monomer to polymer, the process of conversion is known as polymerization. Question number 21. Which nuclear shielding parameters directly provided by the magnetic based heavy concrete? Okay, so when we are talking about heavy concrete, what is happening? It is increasing the attenuation coefficient. So when radiation is coming from one side and it is leaving from the other side. Now, what heavy concrete does, it has the ability to absorb the radiation. So the strength of the signal is decreasing on the other side, and this decrease in the strength of the radiation, it is known as attenuation. Okay, so as when we use like heavy concrete like magnetite, they causes more attenuation in the signal, and that is why they are used for nuclear shielding. Okay, so attenuation is the loss in the strength of the signal, which is possible because of the heavy aggregates that we are using, which are able to absorb the radiation. Now, if we are using steel scrap as aggregate in heavy concrete, what can be the major issue that concrete can face? Can anyone tell me? So since we have very less time left, I will just tell you the answer for all these three questions. So steel scrap, when I'm using, what happens? Steel scrap, it is a scrap, so it has an inconsistent size and shape. Now this inconsistency can affect the compaction and the strength of the concrete. That is one point. And since it is steel, it can show some. It can. Uh, it can be subjected to corrosion, which is also a major durability concern. So that's why the correct answer is D. Question number 23. Which is what is the primary mechanism by which AEC achieves its insulating property? So it is the correct answer will be the option number A. Okay, it is due to the porous matrix formed by the entrapped gases. So we have talked when ASC, it consists tiny air pockets which are formed due to the chemical reaction of the aluminum powder with the calcium hydroxide. Okay, and this pores reduces the thermal conductivity, which gives the AC air aerated concrete a insulating property. Question number 24. Which property is most likely to be compromised in lightweight concrete if aggregates are not pre-saturated? Okay, so this is a very important question. That is a major issue of lightweight concrete, and it is the strength due to internal water absorption. Okay, so what happens when we are talking about aggregate? Lightweight aggregates are highly porous in nature. Now, if there is pores inside the aggregate and we are using that aggregate in a concrete system, so the water absorption capacity of aggregate will be more. And if we are not taking into account the absorbed water by the aggregate, or we are not pre-saturating the aggregate before using, then it can affect the water to cement ratio of my concrete, which can make my concrete dry and less workable, and it may not give me the adequate performance that I needed. So that's why when we talk about lightweight aggregate, the porous nature of aggregate we need to consider while designing. So we need to take equivalent water in the system which can make my aggregate saturated, okay, properly. Okay, now the final topic of this course and in special concrete is the one related to the sustainability or sustainable construction practices, and that is recycled concrete aggregate. So as you can see in the image, tons of CND waste is generated from demolition of old structure. Okay, and if the CND waste are processed properly, we can form what is known as recycled aggregate. So recycled aggregate is produced by recycling construction and demolition waste such as crushed concrete, masonry, bricks, and asphalt in place of using this aggregate in place of natural aggregate. And the aim is to reduce the environmental impact, promote circular economy, and conserve natural resources. So such concrete which is made with recycled aggregate, cement, and water is conventional what we use in normal concrete. But instead of natural aggregates, we use recycled coarse and fine aggregate. Okay, and additionally, we can have some admixture or performance enhancer in terms of super plasticizer or pozzolana if we need. Okay, so this diagram shows the entire process how CND waste is processed to make recycled aggregate. So suppose a building is demolished, the debris is generated. Now this debris can go for use at subways, or it can go as final disposal in some wasteland. However, to avoid this disposal waste generation, what we can do, this debris we can process in industry and we can make recycled aggregate. Okay, now this recycled aggregate, if they are mixed with fine aggregate and certain gravel, some natural aggregate also, and in with cement, all these three things together can help us to make a concrete structure again. So from waste we are making new building, we can say. Okay, and this process will continue to repeat. Now this waste that is generated, the powder portion of that waste, it can also used in cement manufacturing again. So if we can derive the pozzolanic, the reactive part from this powder, we can make the cement also from the recycled material, which can also be used for making concrete structure. Okay, or it can be used for soil stabilization purpose also. So there are different ways in which the entire demolition, construction and demolition waste can be utilized again for building a new structure. Now, though this RC is promoting sustainable construction, there is one major problem with the use of recycled aggregate, and that is the integrity of concrete made with the recycled aggregate, and which result in much lower strength than natural aggregate based concrete. And why this happens? Because of the presence of adhered mortar over the aggregate. So if you see the aggregates that are formed from CND waste, there is already aggregate plus cement paste system that is present over the aggregate. Now the cement paste, what they will do, they will the cement paste is, it is already adhered over the aggregate. So you can see here there is cement paste already present over the aggregate here, but here there is no cement paste present over the aggregate. So what this adhered cement paste or mortar does, it weakens the bonding between new cement. Okay, so suppose this RC I am using again in concreting. So this is my aggregate and I am adding cement plus water. So this cement will plus water will make some cement paste, and this cement paste will try to adhere over the aggregate. Now since there is already mortar present over the aggregate, the cement paste may not be able to bind properly with the aggregate. So the ITZ which is formed over the aggregate, it will be weak. Addition to this, this mortar which is present over the aggregate, this is porous in nature, so it can result in high water absorption and low specific gravity of aggregate that we are using, and all this can result in poor quality aggregate. Okay, so this is one of the major issue with recycled aggregate. To improve this property, we use some certain treatment methods on recycled aggregate, either by eliminating the adhered mortar or by improving the quality of adhered mortar. So you can use some thermal treatment, mechanical treatment, water soaking to eliminate adhered mortar, or we can use some acid soaking or chemical treatment to remove the adhered mortar. Or to improve the quality of adhered mortar, we can use some polymeric treatment or biodispersion, or we can use certain incorporation of pozzolanic material or carbonation. Okay, since adult motor has CH in it. If we add CO2 to the system, CH will react with CO2 to form CaCO3. So that will strengthen the pores that is there in the adult motor, and it will make the adult motor strong. So that is why here carbonation is written. So this is the way, these are the way in which adult motor can be strengthened. And one of this we have described in this figure. So this is again a part of my bachelor's project that I did in IIT Indore. So this is thermomechanical treatment. So you can see here I have mixed recycled aggregate. Okay, I heated those mixed recycled aggregate different temperature ranging from 300 to 800 degrees Celsius in muffle furnace. So you can see this is the crucible in which aggregates are placed, and I'm heating this in a muffle furnace at a very high temperature. So you can see here the temperature is mentioned, it is 789 degree right now inside the furnace. Now after heating, I will take out this crucible out and I will place the aggregate. So once the aggregate is heated, what will happen, the adult mortar will become weak. Now I need to remove this adult mortar, so I will do some mechanical treatment. So I will rub the aggregates using abrasion. Okay, so the abrasion cycle is performed in Los Angeles abrasion machine, and from this debris I will have a clean and adhered mortar free aggregate. Okay, so this aggregate, it will be able to perform better compared to untreated aggregate, and this can lead increase its potential for use in reinforced concrete application for high value purposes also. Okay, so this was all about special purpose concrete that we will discuss today. And with this, I will conclude the week. So we first had an overview of special concrete. Then we talked about high strength concrete and ultra high performance concrete. We talked about self compacting concrete and different testing used for validating self compacting concrete. We had short discussion about fiber reinforced concrete, roller compacted concrete, polymer concrete, composite, heavy concrete, light concrete. And in light concrete, we saw lightweight aggregate concrete, pervious concrete, foam concrete, and AC. And finally, we discussed about recycled aggregate concrete, challenges and remedial measures for them. Okay, thank you.
Sir, I have one question.